right, now we're going to begin chapter 2 and look at section 2.1, quadratic functions and models. Okay, so in this section, we're going to talk about polynomial functions. So we've looked at some polynomial functions before. And so the first one that we've looked at the first one that we looked at was our linear function, and that's f of x is equal to ax plus b. This is our linear functions. We looked at those. Those are straight lines. We have a constant function, f of x is equal to c, where c is just some constant. And then we saw our squaring function in the last section, f of x is equal to x squared, squaring function. These are all examples of what we call polynomial functions. So let's look at the formal definition for a polynomial. Okay, so let n be a non-negative integer, and let a sub n minus 1, down to a sub 1 be real numbers where a sub n is not equal to 0. Then a polynomial can be written in this form here. F of x is equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot, 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 down to a sub 1, x to the first, plus our constant term, a sub 0. We're going to call that our constant term. And this is a polynomial function x with degree n. So the highest exponent is the degree of the polynomial. Okay? And so keep in mind the constant function has a degree of 0. Okay? So if we can recall, f of x is equal to c, we can think of this as x to the 0, because x to the 0, anything to the 0 power is 1. So that's c times 1, which is just my c. So we say it has a degree of 0. Whereas the linear function has a degree of 1. The highest degree is 1. In this section, we're going to focus on what we call second degree polynomials. And so second degree polynomials we're going to call quadratic functions. So here are some different examples of quadratic functions. Okay, and so this is the standard one we see often, x squared plus 6x plus 2, but it might not be expanded. So if I notice in this function, if I were to expand this, it still has a highest degree of 2. Okay, this is a quadratic, this is another quadratic, and this one also has not been expanded. So while these are 1s, once I multiply through, of course we know it will have a degree of 2. So let's look at the formal definition of a quadratic function. If a, b, and c are real numbers and we don't want a to be equal to 0, then f of x is equal to ax squared plus bx plus c. This is a quadratic function. Now notice if a were equal to 0, then I would have 0 times ax squared, which would mean this term would go away, which means it will no longer be quadratic because the highest degree would be 1. So you want to make sure that your a is not equal to 0. That's why I specified. And so if we were to graph these functions, they have a special, this U shape, which we're going to call a parabola. Okay? And so we see parabolas in real life in different things. Think of spoons, satellite dishes, flashlight reflectors. So this is a phenomenon that occurs with quadratic functions often. Okay? So all parabolas are symmetric with respect to what we call the axis of symmetry. Sometimes we just call this the axis. So the axis of symmetry, okay, is the point, is the line, and so it's this line, in this case it's this red line, that when I reflect about this line, I have a mirror image. So it's a reflection kind of about the y, but this line is always on the y-axis. All right, and so the point where this axis meets the actual graph is the vertex of my parabola. So we have the vertex of the parabola. Now, we notice this graph is open upwards. If the a is greater than 0, or we say positive, then my graph is open upwards. So another way to think of this is the leading coefficient of this function, ax squared plus bx plus c, is positive, then we have it open upwards. Okay. Again, I have my axis where it hits the axis is the vertex. If a is less than 0 or negative, or the leading coefficient is negative, my graph points downward. So we saw that in the last section when we were looking at our graphs. If I have a negative in the front of my function, it flipped about the x-axis. Okay, but for parabolas, in general, it means it points downward. So when the leading coefficient is positive, the vertex is the lowest point. But when the leading coefficient is negative, the vertex is the highest point on my graph. So we just repeated this information. You can fill in your slides. When the leading coefficient is positive, our graph opens upward, our parabola opens upward. When the leading coefficient is negative, our parabola opens downward. So let's look at the simplest type of quadratic function. This is when we just have ax squared. F of x is equal to ax squared. So we do not have the bx plus c. All right. This is the graph who has a vertex at the origin, or 0, 0. Okay. And so when a is greater than 0, that vertex, which now is 0, 0, is the minimum, we say, point on the graph. Okay. If the a is less than 0, then that means a negative leading coefficient. Then 0, 0, the vertex, is the maximum point on the graph as shown here. So when sketching the quadratic function, it's always useful to use that squaring function. So if we use this parent function y is equal to x squared as a reference, it's easy for us to graph other functions stemming from this. Okay, so let's look at these graphs here and just use our parent function and see if we can remember how we might graph them. Okay, so for a, if we think of y is equal to x squared as my parent function, what do we say that the 1/3 does? Okay, that is a shrink of the graph. That means that I am going to be pushing this graph down, or in other words, the graph is going to be wider. Okay, and so this is the graph of f of x is equal to 1/3 x squared. And so we see it here a little better than what I've drawn, and this is actually drawn to scale. So we see that we have a little wider, or a shrinking a factor of 1/3. Okay. So now if we look at the parent function of x squared, and we want to graph 2x squared, if we recall again, this is a stretch. So we're pulling the graph, the graph up. And so it's going to be smaller. And so our new function g of x is here. And then it's narrower than our original function. So note from that example that leading coefficient, we call it leading coefficient a, determines where my graph is open. So when the absolute value of a is small, okay, and so it opens, so we say the absolute value of a is less than 1, okay, or we can think of it as between 0 and 1, but we know it has to be positive, okay? Then the graph opens wider, all right, and then when it is larger, or when the absolute value of a is greater than 1, okay, then the graph is smaller. So we saw this before. All right. And so we can use these same things that we've done before with our shifts and transformations to decide what a quadratic might look like. So if we recall, if I have this, the plus shifts to the left and the minus shifts to the right, my original function. And then the plus c shifts up, the minus c shifts down. If I have a negative of the function, it's a reflection about the y-axis, and if it's a negative of the function, it's a reflection about the x-axis. So we can use these transformations to draw some graphs. So let's look at these graphs here. So if we look at the parent function y is equal to x squared, that's in our gray, and we want to produce negative x squared plus 1 is our f of x. All right, so the negative tells me I'm going to have a reflection about the x-axis. All right. And then the +1 tells me I'm going to shift up 1 unit. So this new graph in black is my function. Okay. Likewise, our parent function is x squared. The +2 tells me I'm going to go to the left 2. Okay. And then the -3 says I'm going to go down 2. Okay. And so what do I notice? I have a vertex at -2, -3. And then I have my function. All right. And so we're going to look at this. We're going to stop here and we're going to come back to class next period and discuss the standard form of my quadratic equation.